All right, I'm going to explain the standard deviation. It's actually one of my favorite statistics, so I like to draw it out a bit. Now, the example I'm going to give is a little silly, but I think it really works in helping to explain exactly how it works. We're going to start at the center of your existence, especially now while we're all under confinement, is our home. So here's my house, and of course no house is complete without a little cat in the yard. Now, from my house, center of my existence, I traveled to several places, or at least I used to before I was under quarantine. One of the places that I used to go is, of course, USI. There's the little cone. And from my house to USI is about 6 miles. That's the distance I have to travel to get there. Another place that I go to on the west side is, I don't know, we'll say Home Depot. Sure, why not? I'll pick up some lumber there in the parking lot. Such a great drawing of lumber there. It's about the same distance to Home Depot from my house, also 6 miles. Now, sometimes I actually have to travel to the east side, and I have a little thing for yarn, so I like to go to the craft store. And the craft store is actually a little bit closer to my house. It's about 5 miles away on the east side. And where else do I go on the east side? I don't know. We'll say shoe store. Actually, I never really go to a shoe store, but sure, why not? Let's draw a shoe store. And from my house to the shoe store is a little bit farther there on the east side. It's about 7 miles. All right. Now, if I asked you the total distance that I traveled on all 4 of these trips, you could add up all of these scores. It's 6 plus 6 plus 5 plus 7, right? It's 24 total miles I traveled. What if I asked you the average distance that I traveled? You know, I took 4 trips on average. How far did I travel? Well, you know how to calculate this. It's just a mean. I'm going to take all my distances, I'm going to sum them up and divide by the number of distances. So in this case, it's 24, and then it's divided by 4, because I took 4 trips. Oh, sorry about the little point there. Let me fix it. So it's 24 divided by 4, or 6 miles. So on average, I traveled 6 miles. The average distance of places of interest from my home, my center, is 6 miles. And believe it or not, we just calculated the standard deviation. And you're like, well, wait a minute. No, we just calculated a mean. The standard deviation is a mean. It's measuring average distance of places from the center, except for it's not really places, it's scores from the center. And it's not your home in the center, it's actually the mean that's in the center. So let me just erase all these nice little drawings of buildings that I did, and I'm going to replace them with this symbol for individual scores. Little y sub i's. And all the standard deviation is doing is it's measuring the average distance from the mean to the individual scores in a data set. It's not any more complicated than that. The way that you measure the distance is you just take the individual score and you subtract the mean. Okay, so here's the same drawing of the little house and the little places, except for I've appropriately put in the symbols for the mean in the center and the little y sub i's representing scores on either side. Now, what I want to do is hang values on all of these so I can demonstrate the calculation a little clearer, so I'm going to go ahead and enter the values. Okay, so in my little demonstration here, the mean is equal to 10, and I have 4 scores. I have a 4, a 4, a 15, and a 17. Now, if I want to measure the individual distance from each score from the mean, I'm going to have to take each individual score and subtract the mean. And I always go in that order. So I'm going to start here on the left side, or, the west side of town, if you will. And I'm going to take each individual score and I'm going to subtract the mean. So in this case, it's 4 minus 10, which equals -6. That is the distance. And then I'm going to do the same thing for the next score, which is going to be exactly the same because it's the same score. And then I'm going to do it for the two values that are greater than the mean. So I have 15, and again, it's the score minus the mean in that order, and that equals 5. And then I do it for my last piece of data, which is the score is 17. Having trouble writing the 17. There we go. 17 minus 10. Oops. I'm making a mistake. Okay, we're going to try it again. 7. I don't know why that was so hard. All right. So I have 4 distances total on here. And here's where we get into a little problem. Now, if we want to calculate the average, then what I just told you, I said that, we're going to take the sum of all distances and divide by the number of distances. Well, if I add these all up, -6 plus -6 plus +5 plus +7 gives us a grand total of 0. So 0 divided by 4 equals, well, you can't do it. It's an impossible calculation. And this is because of one of those sneaky little properties of the mean. If you remember, I said that the mean is a balancing point. It's always going to be in the mathematical center of gravity, so that the weight of the scores below the mean is going to exactly equal the weight of the scores above the mean. So if I simply try to add up all the distances, the negatives will always be directly equal to the positives. In other words, the distance below the mean will always exactly equal the distance above the mean. And if it doesn't, it means you've calculated your mean incorrectly. So we have to modify the standard deviation formula just ever so slightly. What we're going to do is, one of the easiest ways to get rid of negative numbers is to simply square it. All right, so we are going to go through and square all these values. So instead of summing up distances, we are going to sum up squared distances, like this. So all I need to do here is plug in all my distances, and I have -6. I'm going to square it, and then I'm going to add that to -6, and I'm going to square it, and I'm going to add that to 5, which also gets squared, and then last I'm going to square the 7. All right, and then just like before, I'm going to divide by the number of distances. I'm just going to write in the values of the square above each one. So -6 squared is 36, -6 squared is 36, -5 squared is 25, 5 squared is 25, and 7 squared is 49. All right? And then what I want to do is I want to add all of those up, and then I'm going to divide by 4. I believe if I did this right, it's 146 divided by 4. And if I divide those two values, oh, I'm almost out of room here. I get roughly 36. Actually, I think technically it's 36.5. Now, this is not average distance. This is average squared distance. Remember, because I squared all the distances in order to get rid of the negative signs. So, if I want to get back to just regular distances, then what I'm going to do is I'm going to take my result here and I'm going to square it, take the square root of it. So the square root of 36 equals 6. And that is the standard deviation for these data. The average distance these 4 scores are from the center, from the mean, is 6. Okay, I'm going to do a final video lesson on the standard deviation using your favorite cat data, same data that we've been using. And here I've posted the entire formula for the standard deviation. The top one in red is for the population. The symbol is small sigma, and the bottom one in blue is for a sample. Now, a couple differences between these two formulas. Unlike the mean, the formulas are slightly different. If you'll notice, for the standard deviation for the population, and this is just a symbol change, but I used mu instead of y bar because I would use a population mean, not a sample mean when I calculated it. But, you know, I'd still use the mean. Now, the other difference you'll see is in the sample standard deviation, in the denominator, it's not n, it's n minus 1. Why do we do that? Well, there's no mathematical reason when we're trying to calculate average distance that we would reduce n, but there is a theoretical reason. Eventually, what we want to do with our statistics from samples is use them to estimate population parameters. And we just assume that whatever we captured in the sample, the variability in our sample that the standard deviation measures, there's going to be even more variability in the population. So what we do is we just make the sample standard deviation just a little bit larger. When we reduce the size of n in the denominator, what that's going to do is it's going to make S, or the standard deviation, slightly larger. So for example, with the cat data, in my sample I have a lady with 22 cats. Now, if I want to use this data to estimate what cat ownership is in the population, then there's probably even more variability in the population when it comes to people having cats. If I have an outlier 22, I guarantee in the population there's somebody with like 100 plus cats. So, by making our sample standard deviation just a wee bit larger, it actually becomes a better estimator for the population. Okay, so enough of that. This is sample data, and I want to demonstrate using the cat ownership variable. So I'm going to go ahead and get rid of the population formula, and I'm just going to rewrite the sample standard deviation formula. And we're just going to go through this step by step. It's not as hairy of a calculation as it actually looks like, and I tend to always lay these things out kind of as a spreadsheet. Okay, so here I've copied it into a little spreadsheet table, and I've got all my scores listed down. They're just in order from low to high, but they're the exact same scores that we have been working with the cat data. Now, when we look at the formula for the standard deviation, whenever you see parentheses, you're always going to do that first, and then you work yourself out. So the very last thing we're going to do when calculating it is take the square root.
So the first thing we want to do is what's inside of the parentheses, and that's take each individual score and subtract the mean. Remember, this is the measure of distance. So we need to get the distance from each individual score from the mean. So we need the mean, and there it is right there. We calculated it in a previous lesson. So it's on average, people have 3 cats. And we're going to take the score and we're going to subtract the mean for each one of these. So I'm going to take 0 minus 3 equals negative 3. And I'm not going to show my work for each one. So negative 3, negative 3, negative 3, negative 2, negative 2, negative 2, negative 1, and positive 19. Now, again, if you did your calculations correctly, if the mean is correct, and you did all your subtraction correctly, then the sum of this column should equal 0. Again, the weight of the negative scores, those scores below the mean, should exactly equal the weight of the scores, or in this case, the single score above the mean. So we have negative 19 and 19, so it equals to 0. Which is why, of course, why we have to square everything. So now I'm just going to take each one of those scores, and if I look at the formula, I've done the subtraction, now I need to square them. So negative 3 squared is, it's not letting me write, there we go, 9, and 9, and 9, and 9. Negative 2 squared is 4, negative 2 squared is 4, and 4. Negative 1 squared is 1. And 19 squared, I had to use a calculator on this one, is 361. All right. And then looking at the formula, it says, all right, now sum up all of those distances. So I'm going to take this column, and I'm going to add up all of those squared distances, and I get 410. So now I can take my 410, and that is the value that goes into the denominator or the numerator here. So I'm just, oops, it's not erasing it. There we go. I'm going to put that value in here because I've squared them all and I've summed them all up, and so I can just enter 410. And then, of course, I have 9 cases, so 9 minus 1 is 8. So 410 divided by 8. And then I'll just go ahead and finish the calculation here. So and then the very last thing that I'm going to do is take the square root of that product, the 410 divided by 8. And you get roughly 7. Technically, it's like 7.14. I don't, use your own rounding rules, whatever makes sense for you. But in this case, the standard deviation is 7. So 51 is square distance, but 7 is the actual value. It's saying that on average, cat ownership varies by about 7 cats. Very technical interpretation of the standard deviation is that average cat ownership varies by 7 cats from the center. An average cat score is 7 cats away from the center. Usually that's not how we say it, but remember it is average distance. But it's measuring differences among people or variability. So typically when we interpret the standard deviation, we talk about it in terms of differences among people. So on average, cat ownership differs person to person by about 7 cats. And as always, we put the units on there as well. And that seems like there's a lot of variability. And again, when we look at the data, the reason why the standard deviation is so large is because we have an outlier. If all we knew about the data, if we didn't know the raw data at all, and all we had was the mean and the standard deviation, we would think that there's just a huge variability out there in the world in terms of cat ownership. And that's because we have an outlier. If you want to, you can calculate the standard deviation without the outlier, but again, remember we never just eliminate data because we don't like it. You can use the interquartile range on this data, and that would probably be a better measure of differences among people, or the range. But the thing about the standard deviation, not only is it affected by outliers, it's just really, really affected by outliers, and here's why. Because the outlier of 22 cats is used twice. It's used once to calculate the mean, and then it's used again to get a distance. And so that makes the effect of outliers on the standard deviation just really, really huge. So one of the main reasons why we run frequency distributions as the first step in data analysis, is what we actually talked about in class, is we want to get typos out of there, mistakes and errors. We want a quick snapshot of the data, but it's also going to point to outliers. And when we see an outlier, then we can make better choices about which statistics to use. The standard deviation just doesn't work very well when you have a huge outlier.